I'm a firm believer in the golf ball effect on port injection. And the golf ball effect is effectively having the dimples that you would see on the golf ball machined into the port wall. And what that does is create a little pocket of air in every dimple, and then the air can just perfectly flow over the top. The problems that we would have with port injection of fuel sticking to the walls of the port, this actually helps the fuel to get ingested by the engine and not stick, and gives you a more efficient burn effectively.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Terry Radbourne from Bourne HPP in the United Kingdom. Terry is a specialist in all things Honda K20, which is quite handy considering these are one of my favourite engines, and I'm going to be milking Terry throughout this particular episode for all of the secrets to building a high-performing, naturally aspirated K20 for very selfish reasons. Obviously, we have a Honda K20 in our CRX endurance car, and I'm always looking for ways to improve the performance, and why reinvent the wheel? Terry's done just about anything and everything you could think of on the K-Series platform, so I'm going to be benefiting from his experience, which means so are you. Now, not only is Terry an expert on the K-Series platform, but he has a really interesting backstory, particularly how he got into engine building, and he's worked for some really big names. Specifically, he's worked for Advanced Engine Research, or AER, and this is a name that a lot of you may not be familiar with, but they build bespoke engines for the likes of LMP1 Le Mans prototype cars, just to name one of the categories they're involved with. They do all of their in-house development of the engine, design, development, dyno testing, etc., and are also very closely linked to Life Racing, the specific ECU that they use, which also now just happens to be Terry's ECU of choice. Following on from this, he also did a stint with Mercedes F1, and it's not too often we get to talk to guests that have experience at this level. And I will add a little caveat here. I'm sure everyone can understand that working at the likes of AER and any of the Formula One teams comes with a bunch of NDAs. Obviously, they can't talk about everything that they were involved with during those times, and you'll notice that during this interview, Terry might seem a little bit evasive on a few of the questions that I'm asking him. My guess is that for very good reasons, he can't talk about everything. So let's just understand that and keep that in the back of your mind while we're going through this interview. Before we get into our interview, for those who are fresh to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune, how to construct wiring harnesses. We also cover race car setup, race driver education, and fabrication, just to name a few of the topics we cover. You can find our entire back catalogue at hpacademy.com/courses. All of our courses are delivered via online high-definition video modules that you can take from anywhere in the world, provided you've got an internet connection, meaning that you can learn from the comfort of your own place and you can learn at your own pace. As a podcast listener, you can use the coupon code podcast75, and that will get you $75 off the purchase of your very first HPA course. We'll put a link to the courses page as well as that coupon code in the show notes. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Terry. Thanks for joining us. Really excited to get into this chat from a selfish standpoint because I'm ready to pick your brains on everything Honda K-Series. But before we get into it, let's find out about your background, as we always do. How did you get interested in cars, motorsport, and engines in the beginning?
So yeah, my background is really straight out of secondary school or high school, thrown into the deep end. I started at a company called Advanced Engine Research in the UK. They specialised in developing blank sheet engines for Le Mans 24-hour, LMP1 and LMP2.
We actually had the privilege to tour Advanced Engine Research's facility, or AER as they're probably more commonly known. And for those who haven't heard that name before, AER is no joke. They are working at the absolute cutting edge of engine development and engine performance, and developing bespoke, clean sheet of paper engines for particular high-level professional motorsport applications, which was really why we were given a tour, but unfortunately we weren't allowed to film anything in the facility. It was a bit of a waste, unfortunately. An exceptional facility. How do you just walk in the door at Advanced Engine Research and get yourself a job? Surely there's a few dots we're missing along the way.
So I think my granddad had a bit of a play with that. So he owned a machine shop that machined heads for Cosworth, and I think he had some link to Mike Lancaster, who's the founder of AER. So as a lot of companies in the UK work, I sort of had a leg up, I suppose, but also had the experience to go in. I probably had 3 or 4 years of looking over my granddad's shoulder CNC machining to start with, which was obviously quite a bit of experience for a 16-year-old to already have. So
definitely,
it was in and hit the ground running, really. So
at this stage, no formal qualifications probably, given your age, but you've got that experience from watching your grandfather obviously doing this high-level machine work for Cosworth. What was the job position when you started at AER? What are you doing there?
It was effectively an apprentice, but we only had a small team of guys at AER right in the early days. This is back in 2003. We had 16 guys to design, develop, build, dyno, track support, and make looms and ECUs for Le Mans. So it was just a 14-hour day was quite usual, and the odd all-nighter in a month was quite normal too. So it was just effectively it was my university. It was the place where I just crammed as much information and learned as much as I could as quickly as I could. And they had all of the facility and projects on to do that. So it was just a mega place to get my grounding and my first entry into engineering.
So if I'm sort of joining all of those dots together correctly, you're getting experience on engine development, so the engineering behind designing and developing an engine. I'm guessing here you're also getting involved with learning about the calibration or mapping of the engines, harness development, and we're also going to talk a bit more detail about it, but actually they developed their own ECU, which ended up becoming Life Racing. So pretty much anything to do with the powertrain itself, you had a hand in that.
Yeah, and I think also one of the biggest fundamentals from AER at the beginning is there was no upstairs, downstairs sort of regime. The big core of the first guys that were in the business, there wasn't engineers versus engine builders. It was just one big team effort. So in larger companies that I've worked in and across the globe now, engineering would be very much split from the shop floor. But in AER in the early days, we would be assembling an engine. The designer would be stood there helping, getting the nuts and bolts out the rack. The guy that was about to map it would be sat in the corner, creating a base calibration, looking at the engine himself, and it was just a team effort. So it was easy to pick up skills in every department very quickly. You could be out in the machine shop at one moment and off, potting a sensor at the next. It was just a team effort effectively, which I think it doesn't really happen in big businesses as much now.
No, I can imagine that would be quite a unique scenario.
Yeah, it was just a mega place to learn.
All right, without getting into too many specifics, and I'm assuming there's a bunch of NDAs around your time at AER, I'm interested if you can give us some high-level understanding of the process that goes into developing an engine from a clean sheet of paper. And where I'm going with this is when you are developing an engine from a production-based factory engine, a lot of the designs are really constrained. The geometry within reason of the engine, the components are already set. Likewise, you're dealing with a production cylinder head, which yes, you can modify, but obviously there are limitations compared with this clean sheet of paper approach, where obviously there will be regulations with a racing class, but so much freedom. I figure it would be very easy to kind of lose your way if you weren't careful and weren't really understanding what the engine needed. So can you give us some insight into how that design process actually goes?
Yeah, I think obviously being involved in a few blank sheet engines now in my career, I think the more that you do, obviously, the more you understand the process. And I think every time now, if I was to take or be involved in a project like that again, is to go straight back to the overview. The overview to make an efficient engine is to not give away cheap energy. Like, you can't give away energy for free. So that is vibration, that is energy into the cooling system. I think really one of the big fundamentals has always been vibration. So before you even start drawing anything in CAD, is to try and understand the harmonics and what is going to go on in the chassis that you're developing the engine for. Obviously, everything that I've ever done from a blank sheet of paper or been involved in has always been stress mounted. So critical speeds of cranks, camshafts, all of that, what I sort of call 1950s physics, all needs to be put in the cooking pot at the beginning, and the big fundamentals of what you're actually going to go and try and achieve with it. But I think, not designing everything in a way to keep cranks away from critical speed, camshafts away from critical speeds, and not creating vibration on a said engine is one of the key or starting features really of the design.
When you're talking about these critical speeds and the vibrational harmonics, are you talking here about making sure that you are not operating at a resonant frequency for the component where those harmonics are sort of amplified and are more likely to result in a failure? Or am I missing the point here?
Yeah, so obviously when a crank is designed in F1 and an F1 engine idles at around 5,000 to 6,000 RPM, and the crank will be designed in a way that all the critical speed is put right down the bottom end of the rev range. So it would normally be on most crankshafts around 3,500 RPM. Obviously, the Mercedes F1 engine that I ended up being involved in towards the end of the latter part of my career rev to 18,000 RPM. So all of the bad harmonic that you're ever going to get from any shaft in the engine is hidden in a point that you're never ever going to see on track or in the garage. So even to the point, if you watch an F1 engine warming up in the garage, the systems engineer will have a little blipper in his hand, and he'll constantly be, while the car's up on the stands, he'll constantly be blipping the engine. And the reason for that is not to do an elaborate warm-up, it's to nullify the vibration and take the vibration out the back of the car, because you have what's called 5 orders of vibration. So the first order, if the first order keeps building and building, it can spread to the second order, the third order. Then all of a sudden components can get stresses on that you don't actually want them to see or experience, and that they don't experience on track, because the rate of acceleration of revs is so fast, you're constantly ripping through them energies, and you're not letting them energies from one component and expand into another.
So essentially, you want to avoid holding the engine at a steady RPM, and that's you're always moving through those frequencies.
Yeah, you're moving through them, but also fundamentally, when you design the engine from scratch, you try and put everything out of the way. So when the engine's actually on track and running, there isn't any critical speed of crankshafts or any component. And a lot of that work that I've done in my career on vibration, a blank sheet engine never happens from the first design. By the time a blank sheet engine goes racing, you'll normally be on engine version D or E. So you would have started with a much bigger, heavier engine with a lot more meat on castings and heads, and you'll slowly work down. And we've always used real high level vibration diagnostic tools to watch. We can watch vibration in all 5 orders. So effectively, as you're leading up through the development, the engine will just get smaller and smaller, slight designs on crank counterweights, a little bit more material there, a little bit off there. And obviously a lot of it is 1950s physics and design, but effectively real world data at 1,000 hertz on vibration sensors paints the picture. I think this is one of the big bits, is through the development stages, if you're data logging correctly, so much can be worked out from the quality of data nowadays. Whereas obviously back in the day, it was all a little bit more feel and like adjust. But nowadays the data doesn't lie, as they say. So
talking about back in the old days, I mean, if you look back in the earlier days of engine development for the likes of Formula One, we didn't have the sort of CAD tools that we've got these days, and also the ability for finite element stress analysis, for example, computational fluid dynamics. None of that was done on a computer back in the day. The technology wasn't there. How important are those software tools for validating a design of a new engine before any single component is ever actually manufactured? Obviously, it's always going to be much, much cheaper to design and test an engine in the virtual world before you actually get to a point of manufacturing it for real.
Yeah, I suppose actually when you look at the price of a modern day F1 engine, it's around £1 million in components. So actually spending more time in CAD land and stress analysis world is actually the more cost effective way, because you're effectively not wrecking £1 million worth of engine. But I think the difference between stress analysis is still in its development stages. I would say you still have to keep feeding back real world data, and everything that works in that world at the moment doesn't necessarily work in the real world just yet. Obviously, one thing that stress analysis can't really do, and when you get back into the orders of vibration, you could be sat on the Mulsanne straight at 6,000 RPM, 100% load, and one part just starts to put a second order or a third order into another, and that leads on to another. And the way I sort of describe it is, when you imagine a drummer playing his drum set, you've got your first order, which is the first big bass drum, and if you kept hitting that hard enough, the vibration would creep, and before you know it, the cymbals are playing.
Sure.
So some of that real world stuff can't actually be simulated just yet. So the virtual world versus the real world, and then slimming the engine down as you get to the actual race spec, you can't just rely on one tool.
Yeah.
You have to sort of do everything in stages. So yeah, effectively, normally in a big engine project like that, you'll start with an engine on the dyno working out combustion analysis, and that engine will pretty much look like it's come out of a tank. It'll be a big, robust piece. The internals are very much what you're going to end up with when you go racing, and you're developing, but casting thicknesses and head thickness, everything's massive to begin with, and then it just gets scaled down as it goes into the car.
So you've got that thick material casting for strength and reliability for a development engine, but obviously that comes at a weight penalty, which you can't have in a race application. So it's about, over the development period of the engine, kind of figuring out where that fine line is between getting the engine light enough to be competitive, but obviously still having the reliability it needs.
Yeah, I think, and also the other bit is we obviously spend so much time on engine dynos. We have all of our vibration analysis on engine dynos, and the engine dyno ends up being a lot harsher than what the engine experience is in the car, especially in F1. When you go and bolt 4 massive bits of rubber around the engine and the harmonics of it, you've actually ended up with 4 massive dampers suppressing the vibration.
Sure, yeah.
So sometimes in the development stages, you can actually scare yourself quite a lot, and probably we end up developing on engine dynos a lot more effectively than what we actually need when it ends up going racing. There's a lot more vibration that obviously a lot gets put into developing engine plates for engine dynos, but effectively you haven't got 4 bits of rubber bolted around it, and you can't get rid of the things that you'll get rid of in the actual car. So sometimes we've seen in the developments that I've been involved in certain engines, we've seen scary moments on engine dynos and had issues with engines that actually, when we put the engine in the car, just don't exist.
Sure.
So a lot of the time, the same vibration analysis software that we've used on the engine dyno for the first tests actually gets bolted straight in the car, and a lot of the scary numbers that we were seeing on the dyno have just gone by the time it goes to the car. So
okay, so the dyno testing in that respect could actually lead you to over-engineer the engine, which in essence actually proves to not be necessary in the race application.
Yeah, and I think especially when we was developing engines with closed loop knot control in the early days, especially on hard mounted engine dynos, we would start to see vibrations creep in and affect the closed loop knock control that didn't actually exist in the real world. And all of a sudden you put it in the car and you've been developing into this real tiny window to try and get the engine to work in, and then the real world,
that window gets a lot wider.
Yeah, which is a nice place to be, I suppose, generally. But
yes, yeah, it normally goes the other way. So yeah, when you get some advantages in the real world on the road or the racetrack, then that's actually a pleasant surprise. Always nice to take advantage of that. You've kind of alluded to your work already in F1, which obviously we don't get too many guests on here who have had hands-on experience in F1. So I want to deal with that in a moment. In terms of the engine development for both AER and Mercedes F1 though, I'm interested, were these engines initially being developed as maybe a single cylinder test mule to sort of do a proof of concept at a cheaper level rather than developing an entire 4-cylinder V8, whatever it might have been, and then once you sort of knew you're on the right path, kind of scaled up to the full number of cylinders, or were you all in right from the start with a complete engine design as intended?
Yeah, no, exactly that. Time at Mercedes before I was there, they was developing a single cylinder. But the big thing with AER is we obviously had decent budget, but we didn't actually have the budget to start the single cylinder stage. I think that is when you go through this whole process, if you can start the single cylinder stage, that's really the ideal place to start to develop piston crown design and effectively even start creating your base map from there. You'll have an idea of how efficient the engine's going to burn, and you can get a lot of data from that. But not every engine project that I've ever been involved with have been able to start there, unfortunately. Pretty much in the AER days, we'd sort of have V1 and V2, and that's sort of what I've brought into what the work we're doing at Bourne HPP. We sort of start with a V1, and you've got some ideas there, and you end up with slight tweaks on pretty much every component, and then it's normally V2 that we end up going racing with. So
yeah, okay, yeah, that makes sense. Now, in terms of internal combustion engines, they are incredibly wasteful. Most of the energy from the fuel that we're burning is sort of going out of the engine in terms of heat and sound, and only a modest amount's actually being turned into mechanical energy. So when we're dealing with a production engine, there's not a lot of levers that we have available that we can pull to really swing the sort of tide in terms of gaining back some of that efficiency. When you're dealing with an engine design from scratch, what flexibility have you got in the design to improve the efficiency? Basically, how much of the energy of the fuel you're actually turning into power at the crankshaft?
Yeah, I mean, like going back to where we started, a lot of the work that I've been involved with has all been around vibration, because vibration is just wasted energy and effectively then wasted fuel. You've had to burn that fuel to create that vibration. So I think a lot of the work that I've done is really trying to nullify vibration and take it out of the engine entirely.
So that vibration, just to break that down, not only are you talking about something that could potentially be damaging to the engine component, but as you're mentioning here, it is also wasteful because some of the energy is being used to create those vibrations.
Yeah, exactly that. And yeah, as your order builds up and vibration across the engine package, it's just more and more energy starts to get wasted. So trying to design components to effectively run at order 1 or 2 and not ever see orders 3, 4 or 5 is what you want to try and achieve, really, to try and make the engine as efficient as you can.
How about in terms of thermal efficiency? I mean, in the aftermarket we see things like thermal barrier coatings for the tops of our piston crowns, even the inside of the combustion chamber as well. Yeah, have you got any input on elements of improving thermal efficiency?
Yeah, there's obviously a lot of coatings that I've played with in my career to do that from a friction loss point of view, and also, as you say, from a thermal point of view. Unfortunately, I don't think I'm allowed to talk about some of the coatings that I've seen. I think that's probably just stepping a little bit too far.
Yeah, fair enough. Suffice to say, I'm guessing if you're not allowed to talk about them, they're effective.
Very effective.
In terms of efficiency and economy, I mean, economy is something we don't really think about too much in a race application, particularly for a sprint race, but endurance racing and particularly for a 24-hour race, economy is incredibly important. It can mean the difference of a pit stop or more over the length of a race. And I think in the aftermarket, enthusiast market, we're used to tuning at sort of lambda targets, maybe in the range of 0.80 for turbocharged engines, maybe 0.85 through to maybe 0.90 or thereabouts for naturally aspirated engines. In the likes of Le Mans, as I understand it, it's pretty common to be on the other side of stoic with your tuning, even with turbocharged applications. Am I on the money there?
Definitely. I think one of the biggest innovations in motorsport and globally has obviously been direct injection. You've just not got as much wasted fuel, and you can effectively have a cleaner burn, is what we call it. You can control the flame front a lot easier. And obviously there's been, not going too in depth, but there's been so much work done even on injector angle. And I think obviously piston design, it's not just one part, it's the whole bit. And I think the big fundamental that I get back to always on engine efficiency is airflow. Like the big overview on all of this is, so we've got direct injection, we've got this, but understanding the airflow of your engine and not wasting or stalling air is really how you pick up massive efficiency gains. Obviously, the big bits with like a straight four engine, for instance, is once you can understand engine scavenging and not creating a secondary pulse in the exhaust. Once you can understand pulsing, I think I've actually seen a few of your posts where you guys have had exhaust gas pressure sensors and you've had sensors post butterfly. So what we'd do in the development stage, once we've got vibration out of the way effectively, is actually map the airflow through the engine. With some turbo applications, you obviously want to stall the air. So creating a piston shape that actually stalls the air on top of the piston for an amount of time to actually cleanly burn all of the particles of air that you've managed to get into the engine through the inlet valve, that obviously increases efficiency. So the big overview, without going too in depth and getting myself in trouble, really is airflow. And once, obviously, the sensors that we have at that level are 1,000 times a second measurement of airflow or higher.
Yeah.
And the actual data that you see in the dyno cell will show you what the airflow is doing.
You've just dropped a number of sort of pretty technical elements into conversation there. And I just want to come back a step. So I mentioned tuning on the lean side of stoic, which for the enthusiast market we don't generally do. And if we're talking about economy at cruise in a road-driven car, typically we look at a production car, it's going to be sort of gently moving backwards and forwards across the stoic air-fuel ratio, 14.7 to 1, lambda 1.0. And most people think that that's for efficiency and economy. The reality is that makes the catalytic converter work, which gives good emissions, which for an OE production engine is really the be-all and end-all. If it doesn't meet emissions requirements, all bets are off. So if we take the tuning outside of the emissions regulations, we can see an improvement in fuel economy by tuning leaner than stoic. And I'm talking still here about cruise conditions. The limitation sort of comes in at some point as we go leaner and leaner, particularly with a port injected engine. We get to a point where we can't reliably light off the fuel air charge. Basically, it just gets too difficult to reliably ignite it, and we start running into problems with misfire. So when you talked about the direct injection here and sort of the airflow, connecting these dots, if I'm getting this right, you're talking about basically managing the sort of fuel air charge, so you've got a rich enough fuel air charge around the spark plug so that it can be reliably ignited even when the overall air fuel ratio is lean.
Yeah, effectively. And I think obviously the big word in all of this is atomization. It's how efficiently can you split the fuel particles and mix them quite quickly with the air, and obviously split the particles into the air. Like so many inefficient engines end up with big blobs of fuel, especially port injection engines, big blobs of fuel running down, and you would actually see with a fast lambda reading, you would see your combustion waving effectively. the atomisation just isn't as pure as what you can effectively get to with direct injection.
Let's just talk about that element for a moment then on its own, because again, we're getting into sort of areas here which we haven't discussed on the podcast, and I think it's sort of areas where there's misconceptions and misinformation. I think most people casually interested in fuel injection and tuning would think that, you know, we get this nicely atomized mist of fuel being delivered by our port fuel injector, and that goes into the combustion chamber and it burns beautifully. The reality is somewhat different because, you know, we've only got a modest period of time with a port-injected engine where we will be injecting fuel with the inlet valve open. Obviously, the intake valve is going to be closed for a reasonable period of the engine's operation. So with that in mind, once we're sort of up in the injector duty cycle range, at some point we will be injecting fuel against the back of a closed valve, which on face value seems completely counterintuitive. The reality is, at least as I've sort of studied it, seen it and understood it, is once the engine is actually at operating temperature, the port wall is obviously hot, the back of the valve is hot, so when we're spraying the fuel and it's sitting on that port wall and the back of the closed valve, it actually vaporizes, and then when the intake valve opens on the next intake stroke, we're actually ingesting fuel vapor as opposed to atomized fuel, the vapor being easier to burn even compared to finely atomized fuel?
Yeah, no, exactly. And obviously the direct injection gets around losing fuel on the inlet valve. And like a lot of misconception, I think, from experience that I've had, is a lot of people back in the old days went to polished ports.
Yep.
And actually what a polished port does with a port injector is you end up with, as I was describing before, these big blobs of fuel, and your burn's just not consistent. So when you are trying to target these much leaner lambda targets, you need to make sure that your fuel delivery is exactly the same every time. And obviously that is really the fundamentals of direct injection. Your consistency of fuel delivery is absolutely perfect, or as perfect as it's going to get. And going back to port injection, there's just the delivery just isn't the same. You end up with, you know, sometimes it's perfect and you meet your lambda target, sometimes a big blob of fuel runs down your polished port. Obviously, this is work that I've done outside of big companies, but I am a firm believer in the golf ball effect on port injection. We've seen some real big movements with the golf ball effect, and the golf ball effect is effectively having the dimples that you would see on the golf ball impregnated into or machined into the port wall. And what that does is create a little pocket of air in every dimple, and then the air can just perfectly flow over the top. But then we've also seen that with the problems that we would have with port injection of fuel sticking to the walls of the port, this actually helps the fuel to get ingested by the engine and not stick, and gives you a more efficient and burn effectively.
Okay, a couple aspects I just want to come back and talk about there. Just about port injected engines with fuel basically forming, I think you mentioned globules, basically pooling out and then dripping into the cylinder. And again, I think the misconception here is that's not happening. Well, it absolutely is, irrespective if you've got a perfect sort of mirror smooth port wall. There is always going to be some level of fuel pooling out on the port wall. This is one of the reasons why we need transient enrichment compensation in our ECUs, so that as we're changing throttle butterfly angle, which involves changing the airspeed and also, importantly, the manifold pressure in the port, that affects the amount of the fuel mass that forms that pool of fuel on the wall. And it's always being topped up by the injector and then at the same time dripping into the cylinder. But that key point there, dripping into the cylinder, the fuel in that form is not really easily combustible. So it's kind of a bit of a waste. So there's that element there. But importantly, I just want to dig into this golf ball or dimple port effect, because every time we post anything about this, we get slammed with a lot of people thinking this is super controversial. I'll admit I don't really have a dog in this fight, and I haven't actually seen any solid results back to back with a conventional CNC port versus a dimple port, what that looks like on a flow bench, and then most importantly, what that actually looks like on the dyno. And we know that the flow bench numbers for head porting don't always directly correlate with real world results on the dyno. So have you got that sort of data? Can you give us some insight into what that looks like?
So when it comes to cylinder head flow benches, it's really not something in my career that I've really got or spent too much time with. So effectively, we would design a cylinder head, or we would make a new port at Bourne HPP, and we would basically put it on the flow rig just to get a rough number. Anytime we see around 300 CFM, generally we're fine. Like, we'll start moving onto the engine, and obviously the experience that I've got, like we touched on before, with actually looking at pressure sensors across the engine airflow. And if you want to go to the next level, having an in-cylinder pressure sensor. So we would have a pressure sensor after the butterfly. We would have in-cylinder pressure sensing, and then a sensor in every exhaust bolt. And then you can really map out what the airflow is doing across the engine. In my experience, the old school way of using head flow rigs, we're sort of past that. That's just generally a check for us, especially if we've created a new port shape and done some of the porting by hand. We would use a flow rig to just make sure, on a Honda, for instance, all 4 of our ports are roughly flowing the same, and we haven't had any issues with the machine inside. So that's really just a check. But the proper work now is actually done at Bourne HPP on the engine dyno and watching airflow through the engine. I think coming back to that port injection efficiency and really getting the atomisation to work, the big bit that we haven't touched on is secondary injection. So everything that I've done in my career with NA and turbocharged engines, we've always had 2-stage injection effectively. So we've had one injector quite close to the inlet valve in the trumpet. We've had that at low speed, so we'd use that to fire the engine up. And generally around 3,500, 4,000 RPM, we start to blend to the set of injectors that we have at the end of the trumpet. And obviously running an injector at the end of the trumpet really encourages the atomisation. So it really helps you to blend the fuel perfectly with the particles of air. And in my mind, I always see the particle of air and the fuel attaching, and it sort of goes down in their little partners 2 by 2 and that's really where we want to get to. I suppose it's my analogy in my head, but
yeah, no, that makes perfect sense. There's a couple more bits I want to talk about on that, but before we kind of get sidetracked, just coming back to the dimple port versus conventional, do you have any kind of dyno numbers, even kind of a rough rule of thumb of what you'd expect from the improvement?
So I think you can get too engulfed in the actual airflow of the port. I think going back to the secondary injection and the atomisation as an overview, if you look at the atomisation of the fuel and creating a very powerful, effective engine or efficient engine, if you can get the atomisation right, the airflow isn't as critical. The two are the same effectively. If you can mix your air with your fuel properly and actually have a decent flow. But I just think a lot of people get stuck on flowing cylinder heads to try and produce power. But that's an engine builder thing to do. But when you've been involved in all aspects, you understand actually I need a really efficient burn to create power and make an efficient engine. And obviously what we touched on before, I need an engine that doesn't vibrate and doesn't go past all the tour vibration. And when you add all of these aspects in, your mind comes away from the head flow rig. I think you start touching on so many other areas, and obviously exhaust length is such a critical thing, and we touched on it earlier. But
well, I think ultimately you can't consider any element of a competition engine in isolation. It is the sum of its parts, so you need to consider every element and make sure that they're all working in harmony. Otherwise you're kind of dead in the water, I believe. Just coming back again to port injection versus direct injection, you've sort of talked about this atomisation using secondary injection, maybe outside of the inlet trumpets to make sure. I think what you're getting at here is the atomisation is important, but you've sort of talked about the mixing of the air and the fuel. So getting what I'd refer to as a homogeneous air-fuel mixture, which simply means that once the air fuel charges inside of the cylinder, basically no matter where we are inside the cylinder, we've got the same air-fuel ratio. Again, I think that's an assumption, but it's not always the case. Now that's great. However, coming back to what I was talking about with lean burn before, with a homogeneous charge, once we get to a sort of a lean air-fuel ratio, at some point we start running into problems with reliably igniting that off. And again, I'm sort of stretching a little bit outside of my own experience level here, but at least I do a lot of reading as I understand it with direct injection. We can design the injection around a stratified charge design where instead of having that homogeneous air-fuel ratio where everywhere in the cylinder the air-fuel ratio is the same, we can actually purposely design a richer air-fuel ratio kernel around the spark plug, which will promote better combustion, ignitability. And then elsewhere in the combustion chamber, we've actually got a much leaner air-fuel ratio. So the overall air-fuel ratio is quite lean, yet we're still getting reliable combustion. Am I on the money with that?
Yeah, so there's obviously a lot of tech that I can't touch on, spark plug tech in the higher levels, and yeah, sort of splitting the spark charge across the cylinder and making sure that we ignite all four corners of the piston is critical, but also piston shape and design. So this isn't really, I'm not really giving too much away here to say the bold piston was designed or really come to market in the Group B rally days. And the whole bold piston design, as much as we're trying to lose compression ratio in a turbocharged engine, the actual bold design is to actually stall the air and create a sort of sweeping air mixture on top of and try and force the combustion to as far to the center of the piston as you can. So effectively, when you want to go to these lean burn states and you want to start running over lambda 1, there's so many parts that come in, but actual piston design and shape on top of the crown is fundamental.
Can you give us some indication when we're talking about leaner than lambda 1, what sort of targets are you actually using in an endurance turbocharged Le Mans engine, if you can?
So I always go back to component control. It just depends what's going on and what scenario of the race that you're in, but we'd always have lean burn strategies. We'd sometimes have component control strategies, which effectively sometimes you just want to start laying some carbon on top of the piston. So go back to the big overview. It's very hard to have detonation if you're constantly laying a layer of carbon one after the other. So the perfect map engine has that lovely grey layer of carbon on, and what that generally means is that you're laying a layer of carbon on your flame front and then you're burning it off. You're relaying and burning off. And some stages we might know from knock, or we might know from very in cylinder pressure sensors that we're starting to lose our carbon front and that we can't run to these lean lambda targets, or there might be something else going on in the engine's health, and we would come back to a component control map or a much richer burn. But generally, if the engine health is right and we're not in the 24th hour of Le Mans, we can generally run with DI, we can run over lambda 1.
Okay. At that point, is it safe to assume that you are giving away a little bit of power and sort of sacrificing that for the benefit of improved fuel economy? Generally, if we sort of take a conventional road car engine and we literally held it at 6,000, 7,000 RPM and we just did a sweep of lambda from, let's say, 0.70 through to 1.1, we're going to find that it's going to make peak power, let's say, at 0.85, maybe 0.90, and either side of that, the power is going to drop away. Am I right in assuming that there's no magic here and we see a similar kind of relationship between power and lambda targets in a purpose-built race engine?
Oh, for sure, yeah. And obviously the big overview to come back to the car as a whole is weight. So a lot of the time you may not carry as much fuel and you'd always make more power with a richer burn, of course. And like you were saying, targeting your 8.5s and your 8.6s is normally the way to go, especially on the turbocharged application, because you've still got a bit of component control in there. And you're still, when I say component control, you're cooling the piston crown. You've got enough fuel to burn and to cool. But when you're at the end of a 2-hour stint at Le Mans and you haven't wanted to carry you don't want all that weight in the car, yeah, effectively you would start to run a leaner lambda target. And you probably hear on the F1 radio a lot of time the term lift and coast used. in F1. And obviously what that means is they're effectively getting to the end of the straight and lifting a lot earlier and getting onto the brakes a lot sooner. But there's a little period from when an F1 car lifts to getting on the brakes that it's charging the energy recovery system as well, which is another aspect of the power unit. So effectively you've brought more energy out of the turbo and the K, and you've got that on your next corner exit. So yeah, there's just different scenarios, and generally on an LMP engine we'll probably have around, I don't know, sort of 48 different cow selections and strategies. So you might generally have 4 to 5 main fuel maps that you can select for a 2-hour stint.
Okay.
And it just all depends. Another thing is, if you're at a point of the stint and you're racing and you've got the fuel on board, you're obviously, but the strategies are obviously through a 24-hour race are here all over the place, really. So you just need the tools within the cow switches, because one thing that you can't do at Le Mans, which we actually have capability to do, is map live. Like obviously a lot of stuff can be done. We have live telemetry coming back one way, and you could, in theory, map a car live on circuit, but there's regulations at Le Mans and in F1 that prohibit you from mapping the car live. So all of these strategies have to be built into the cow switch to navigate yourself through the 2-hour stint on the tyre and also the 24-hour race.
Maybe that's a good thing. 23 hours into a 24-hour race, I can imagine the engineers would be running on a lot of caffeine, a lot of Red Bulls, and probably very little sleep. So maybe the live mapping at that point might be maybe counterproductive when you press the wrong key accidentally. In terms of managing all of those different calibrations, though, obviously the driver is probably not trying to concentrate on 24 different map strategies and which to choose and when to choose them. He's probably wanting to just drive the damn car and race the cars around him. So does that come down to you or an engineer like yourself at the track, looking at all of the data, looking at the fuel burn, looking at the relative speeds to the cars around and deciding when to change to a different strategy and what that strategy would be?
Yeah, for sure. There's a lot of coaching on switch positions. So you would obviously have your switch positions for engine control. You'd have your switch positions for traction control. And then especially with the AER engines at Le Mans, we had different settings for anti-lag. So we was running anti-lag at Le Mans, and we'd have different variations of that strategy, some harsher than others. So yeah, there is, you try and build. You're going to war effectively when you go and do Le Mans, and you're trying to build as many strategies and scenarios into the cow switches to get yourself through. And obviously a lot of that knowledge and strategies get built in pre-season testing and the races leading up to and after Le Mans. So much time is spent in them areas and developing. So just getting the first blank sheet engine off the dyno, the work then just starts, really. It's quite a lot of work up to that stage to get a reliable engine, and then you get to the circuit and all of them strategies and mapping scenarios, all that the work is, it's a big task.
No doubt. All right, I mean, we could talk probably for another hour about Le Mans and AER, but let's move along. Obviously, pretty interesting to talk about your time with Mercedes F1, and I'll just preempt this for our listeners. Obviously, most people could understand that anyone involved in F1, there's not a lot that can be talked about openly. So we'll respect the fact that you're probably not going to be able to dive too deep into any of these elements. But for a start, how do you even get invited to go and work at Mercedes F1? How did that come about, that opportunity?
Obviously, went over to Mercedes was when the V6 turbo engine was being developed, and my experience at AER developing turbocharged engines for Le Mans, my CV sort of had what they wanted at the time, I would say. So a random phone call in my dad's kitchen, I was literally just making some toast. The phone rang, and you've been invited for an interview at Mercedes HPP. And yeah, it was a bit of a surreal feeling.
I would assume that conventionally you're not going to get a foot in the door at that level in a Formula One team, any Formula One team, without a engineering background and degrees. Would that be typical?
There's obviously there's varied jobs within the factory. So, you've got your engine builders, you've got your wiremen building looms, and generally the engine builders and wiremen wouldn't all have a degree. Obviously, it helps to get your foot in the door. Some of them have just got experience, like myself. I had the experience, and I've been there and got the t-shirt, and that's what helped me to get in. But the conventional way to get there is to do at least a bachelor's degree for 3 years and then move on. And a lot of universities now, especially in the UK, have really great motorsport degrees, and obviously there's Formula students, so a lot of people migrate through the university, do Formula student, and that is their intro. A lot of the F1 teams have sort of got guys in universities to bring them guys on board, so it's quite a nice thing in the UK. There's quite a lot of opportunity, which is great.
Yeah, definitely. I mean, obviously the hub of professional motorsport at the upper levels for sure. So what was your position at Mercedes? What were you actually doing on the day-to-day?
So I sort of I had the ability to go through the factory, so I was there for 2 years. Started off in an engine strip and diagnostics, which is basically taking engines that have been at the track and taking them apart and sort of looking at reliability aspects of the engine effectively. And then, the other stages of my career there, I was in what is known as energy recovery now. Obviously, when I started at Mercedes, energy recovery was a very new thing. We had KERS at that stage, but energy recovery was a whole nother chapter in engineering. So I was involved in energy recovery, the development of it, and then I had the opportunity to go trackside with the energy recovery unit as well, and sort of help trackside operations and the first test developments and races of that setup.
Can you maybe give us a quick rundown on how that energy recovery works for those who maybe aren't F1 fanatics?
Yeah, so effectively the front of an F1 engine is gear driven. You'll have it's kind of like a elaborate alternator on the side, which is called the K. So when the car's braking, the engine is putting energy into the K, and the K is creating electricity like an alternator and storing energy in the battery pack, which is underneath the driver's seat. It's also the same with what we call the H. So you've got a motor or an alternator on the outside of a turbo, and that is creating electricity and storing it into the battery pack. It's like a three-phase connector to the battery pack, and once the battery's stored, or when you want to deploy the energy from the battery pack, it actually comes back down them same lines that have charged the battery pack and then turns its electrical energy into power, and the K puts power back into the drivetrain on the front of the engine, and then the power that comes up to the H helps to spin the turbo. So effectively you have no lag, because you constantly have a turbo that is up at your perfect operating speed.
Now, from what I understand as well, the MGU-H that you're just talking about, the turbocharger element, that's being removed from the 2026 regulations, is that right? But the MGU-K is being retained, and that's actually being made more powerful for the 2026 regulations, as I understand it.
Yeah, I think there's actually a lot more engineering possibly that goes into the H, which would probably raise budgets, for everybody. So maybe that's a cost cap, but I'm not, I've been out of F1 for a couple of years now, so.
Sure. One sort of side of that's always interested me is looking at it back when I was younger, watching F1 back in the V12, V10 days. It seemed like back then technology from motorsport did sort of trickle down into OE, and that was kind of like Formula 1 or professional level motorsport was kind of the breeding ground for some of these new strategies, technologies, etc. These days, I don't know if I could say the same, and sort of that MGU-H, at least to the best of my knowledge, hasn't actually made it to production level cars, except for that AMG1, which is a bit of a, sort of a niche case study anyway. Are you aware of that technology being used anywhere in production cars?
No, I haven't really seen it anywhere, to be honest. Obviously, it's not cheap technology, so I would say that's probably just the price restraints. A lot of naturally aspirated tech can effectively just go straight back in, but when you come to complex electrical systems, so it's not just the battery pack and the MGU, it's actually the control electronics as well to control all of that. By the time you add that whole package up, I just suppose it's something that's out of the price cap of a general road car.
In terms of the way the MGU-K MGU-K is used by the driver. I'm interested, can you give us some insight into sort of how much of this is automated? I'm guessing here at least you sort of alluded to the fact that under braking it's charging, but we also see that the driver can, at least as I understand it, purposely harvest energy, basically sacrifice some of the power of the engine under full power acceleration to actually purposely charge the battery so that they can deploy at a time that's, giving them a strategy advantage. Can you talk us through a little bit of that?
Yeah, I don't know how in depth I can go in it, but I would say a lot of the MGU-K power is normally deployed on corner exit. So you have such a precise power deployment that you can deploy energy per corner exit and ultimately dictate your tyre slip. So it can be used in different ways. Sometimes it will be used at the top end of the rev range, but a lot of the time it will be used to save the rear tyre effectively, and you bring the power in from the MGU-K on corner exit and then phase the ICE or the internal combustion engine in over the top and bring the power in. And obviously that deployment, we're talking 80 milliseconds. It's a very short amount of time that the MGU-K is being deployed there, and in the engine phase is quite quick, but in data it obviously looks a lot bigger. But when you're talking about the tyre deg that we had and them restrictions on Pirellis, your really power deployment becomes the part that wins your races effectively. And that's been sort of a core of my work with my mapping that I do at Bourne HPP with Life Racing, is understanding or seeing firsthand how to deploy the power. Once you have all of this power, it's really about getting it down to the tyre. And there's a lot of sensors that we can put around a modern car nowadays to actually work out our rear slip and actually to a precise percentage know how much power we need to deploy.
I think really it just comes down to just another area where, for those who are casually involved in maybe the odd track day in their road car, particularly if they're still on a dot road tyre, you miss a lot of the nuance of what happens in particularly endurance style racing, where it's not about the driver going 10 tenths and getting the quickest lap time that they can. Like, that would be great for maybe 1 or 2 laps, but particular over a long stint, a couple of hours or whatever it might be, you'd end up with the tyre degradation through the roof, and you'll be fast for a couple of laps, maybe 5 laps, and then the tyres will just be completely rinsed and your lap time's gone. So it's about managing the tyre degradation and managing the amount of energy that you're putting into the tyre so that the tyre has still got some life left at the end of your stint, correct?
Correct. And also going back to where we started at the beginning and fuel efficiency across an engine, to actually try and make the car efficient through 24 hours, any rear tyre slip that you see is wasted fuel and engine energy. So actually what you're doing for a 2-hour stint with a power unit is effectively you're turning the power down. You're constantly controlling and dressing the power out. As the tyre deg goes up, you're just fettling out ignition, however you want to do it, fuel, to try and sometimes go into a leaner burn strategy will actually give you, like we've spoke about, you lose power. You might run a leaner burn to save the tyre because effectively you might have knocked out 60 foot-pound of torque at corner exit 3, and that's what you've needed to save the tyre. So, and actually also you're then saving fuel. So that's where these strategies that we build earlier in the projects will come to your favour at the end of a stint generally.
I think we probably need to move on from your background. Like, this is probably the longest discussion around someone's background I've had on the podcast, but your background is obviously somewhat unique, so I think that's justifiable, and definitely has been some really interesting insight that you've given us there. But sort of let's fill in now from leaving Mercedes F1 to founding Bourne HPP. How did that all look?
Yeah, so obviously I'm like you, always looking at every sector, and I had a mega time at Mercedes HPP, but I saw that Life Racing were developing some cheaper ECUs, and also they had the GDI4 at that time, which you can actually utilize direct injection at a decent cost price. I think a GDI4 is around the £1,800 mark. So all of a sudden, all of this learning that I had done for 2 years in F1, there was the tools available to go and take this to all other levels of motorsport. And when you've done what I've done in my career, I think the next natural step was to create my own engine company and tuning company. So, there's been some massive hurdles to get around, but obviously one of the big bits that made it easy to make that transition into having my business was having them tools to go and do the job that I'd done my whole career and be able to offer it to the lower levels effectively.
I'm going to come back to life racing in a bit more detail, but before we do that, just give us the 30,000 foot view of what HPP or Bourne HPP looks like today. Talking here size, location, number of staff.
So we're a 4-man team at the moment, and our skill set, like we try and do everything with them 4 guys. So we've got a bit of design, we've got engine build, which is obviously the fundamental way that we make money at Bourne HPP is selling crate engines. As we touched on before, we started our business around the Honda K20 engine because it's just so widely used and such a good engine. When you go back to that blank sheet engine design and you open up a K20, you're like, yeah, I've got the ingredients for the recipe to start with here. So it was obviously the engine, and I've got a lot of passion for it. So it was the engine to start the business on. But yeah, effectively it's creating very efficient high power units and incorporating like a whole package to the customer. So we're not just an engine builder. We'll build engine harnesses, we'll supply ECUs, we've got an in-house bench dyno where we'll build the calibrations, and then we'll go out on circuit and track support them. So my real role is, I suppose, customer liaison, and I get involved quite heavily in the mapping and the track support side. I've got a couple of really good engine builders with us as well. So, we sort of tick all the boxes with a small team.
All right. Well, obviously, I want to dive into the K20 and pick your brains for as much as I can for my own selfish requirements, as I mentioned at the start. But before we do that, just bring it back to life racing. And this really was born out of advanced engine research. So coming back to that point at AER, why did AER decide that the current offerings of ECU on the market weren't up to what they needed? It must be a massive operation to not only be designing these ground up bespoke race engines, but also then to design and develop your own engine management system.
I think it sort of actually happened the other way around for Mike Lancaster, who's the founder. So he started a company called Pectel with Simon Phillips, and then they went their separate ways, and Pectel ended up becoming Cosworth Electronics, and Mike Lancaster ended up they both left with the same DNA in their heads of what they'd created.
Which is why if you look at Pectel or Cosworth versus a Life Racing or Cyvex, there's a very sort of obvious, consistency between the brands or the products, correct?
Yeah, definitely. Yeah, it's even how it's all laid out on the screen and how you get through branches. I think all of that was done right at the beginning, and them guys are sort of the first brainchilds behind it. Really, a lot of aftermarket ECUs after Pectel have sort of followed that same layout, really. So I think that was the core, really. That was the first seed there. And the actual engine side of AER come after. Mike supplied ECUs to Nissan, and they ended up winning British Touring Car Championship with Mike's sort of Pectel ECU. And then that Nissan relationship grew. The first big contract that Advanced Engine Research got was the Nissan World Series, it was sort of 2 down from F1. It was a feeder. I think Sebastian Vettel won it one year. So, it was a big championship and a big engine project to be involved with. And we developed the Nissan 350Z engine into a sort of 480 horsepower race engine. But it was a one-make championship. So it was all of our engine. That was the first life ECUs run that championship. So yeah, I think we didn't ever get to the point where there wasn't something on the aftermarket for us at that stage. It was just, the founder had already come from the ECU into the engine.
Yeah, obviously that makes sense. I'm sorry, I'm losing track of my ECU history there because, as you mentioned that, I did realise that life was born out of Pectel. So yeah, thanks for clearing that up. What is it in your experience? Obviously, you've been using life racing products for a fair while now. What is it in your opinion that separates them from other ECUs that are out there on the market at similar price points and capability points?
There's not a massive separation. I think the way that life racing has controlled Lambda and some of the more detailed strategies that we would have developed at Le Mans, our closed loop knock control in life racing. There's so many elements that are really, really good in the ECU and probably better than others. But, there might be other ECUs out there that do certain aspects of the cow better. I don't really know. I think for me, it's my tool effectively. Like from the age of 16, I've grown up on dynos at AER mapping with life racing and spent a lot of time with Mark Colby that developed the software. So, he was the original coder for Pectel and then moved to life racing. So it's just my tool. If I'm going to go to war, it's my weapon of choice effectively.
I think that sort of mirrors what I've said on the podcast a number of times. If we look at two capable ECUs and you are just looking at power and torque capability, I mean, essentially within reason, you give the engine the same amount of fuel and the same ignition timing, it's going to produce the same power. So we're at a point now where any high-end ECU is going to be able to do a good job of the fundamentals, physically running the engine. But it's the subtleties around some of the strategies which I think are where those differences creep in. And again, I've said time and time again, you can have 5 ECUs that all have traction control. And I put traction control here in air quotes because there's levels to this, and traction control that's going to be effective in when you races at Le Mans is very different to a traction control on a lower end product, which yes, it'll stop the wheels from spinning, but also you're going to lose 3-4 tenths of a second through that particular corner exit as a result of this overbearing traction control. And multiply that by closed loop knock control, as you mentioned, lambda control, and every other element that these modern ECUs use. The other side of this, which is really easy to overlook, is I know a lot of people, I kind of bring this back to my experience through my old shop. They'd turn up, looking for an ECU for their project car, and maybe they've sort of trawled some forums and they've seen success with XYZ brand. And maybe that's a brand that I, as a tuner, have never seen before. And they're adamant, that's the one they want. Well, yeah, again, we come back to the fact that if it's a capable ECU, yeah, it'll make the power and the torque. That's no problem. But me, as a tuner, I know a different brand intimately, like you do with life racing. So if the customer actually takes your advice and goes with a product that you know inside and out, you're going to be able to get a better result in less time. You're going to be able to support that product better. End result is happier customer, car that makes great power and torque, great drivability, everyone's happy with the result, and probably ultimately they're going to spend less money with you. Does that sort of match your experience with the reality?
Oh, exactly that. I mean, it all comes back to efficiency at every level, and obviously the customer's pocket, and trying to be as efficient as you can with their spending is one of the main principles that we've adopted at Bourne HPP. It's very difficult. So having life racing as my tool, we've built a lot of base maps for different engines, and in the end you can get the base map so good that it is just tweaking per new engine. And obviously a lot of what we've done as well is building engine specs, so we're delivering the same engine package time and time again to multiple Tudor customers, and it actually saves money. Over 10 customers, you're supplying that one developed engine and map for a particular chassis, and that's what we've tried to achieve, is to try and give the best product for the least amount of capital when times are tough out there in the world. To try and keep everyone racing and still having the equipment to be at the front is obviously the technical challenge that we're facing now.
Yeah, definitely. Now, we have had Ryan from Syvex on the podcast previously, so we might link to that show if people want to go a bit deeper. But just with the sort of differences or comparisons, I guess, between Syvex, which is born out of life racing as well, can you give us a quick overview of what life racing and Syvex are, how they relate to each other and the differences?
Yeah, I mean, they're fundamentally exactly the same code. The reason that Syvex was born was because when I was at Advanced Engine Research, we just didn't have the manpower or the need to go to the aftermarket. Everything we was doing with life racing at the time was all developed, like sort of built around our Le Mans project, and that was AER's core business, was American Le Mans series, and so we didn't want to go down that aftermarket route and deal there. So Cyvex was born. I think it was Charlie that come over and saw the capability of the Life Racing ECU, and then Cyvex was there. And yeah, I've had the pleasure of working with Ryan. He's a very knowledgeable guy, and what they've done in that world is just mega. And it's also given me, it was one of the other parts of setting up Bourne HPP, is that they already had all of these. So we are a Cyvex dealer now as well, but they already had all these great plug and play management systems that when we're out just doing the job, you can just buy off the shelf, plug in, and off you go. And it is my tool. It's how my mind works in engine management, is from a young age has been how Life Racing set out. It's just ingrained in me now. So it was such a mega thing.
So essentially, the focus of Life Racing is on the professional level motorsport, no real sort of direct support for the enthusiast level aftermarket, and they've left Cyvex to basically fill in that void in the enthusiast market.
Yeah, and I think in the early stages of Life Racing, the professional world of motorsport was its biggest customer. But I actually think Cyvex are doing much bigger numbers now. They've managed to take the brand globally, and it's well respected across the globe now. And I think there's more ECUs getting sold through there.
And I guess it makes sense. You just look at the numbers, that there is always going to be a limited number of teams operating at that highest echelon of professional motorsport, but there's hundreds of thousands, if not millions, of enthusiasts out there who need ECUs to make their cars run. I mean, I guess, getting a little off topic, but the focus there also needs to be considered. If Life Racing had sort of dived after that enthusiast market as well, yeah, they'd be selling a whole lot more ECUs, but the tech support nightmare that would bring could also be very difficult to manage. So Cyvex have kind of taken on that role. I just wanted to interrupt our interview with Terry here and talk about a package of courses that we've put together. It's going to be perfect for anyone who's enjoying our interview so far. And that is our Engine Building Starter Package. This package of courses is normally $299. Using the coupon code Bourne HPP 100, that'll get you $100 off, bring it down to just $199. This package of courses starts with our Engine Building Fundamentals course, which will teach you the fundamentals of how the four-stroke engine works, all of the components inside. You'll learn about the machining operations that we typically need when we're building a performance engine, which is really important because it will help you to speak the same language as your engine machinist. You'll also learn about the specialist tools and measuring equipment that you're going to need to build engines. Moving on from this, we're including our practical engine building course, and this builds on the knowledge taught in our fundamentals course. This time you'll learn the practical skills that you're going to need to understand when you're building your own engine. We've also broken the engine building process down into the HPA 10-step process, and this makes it really quick and easy to build your engines. Each of those individual steps is relatively quick and simple to complete, and in no time you've got to the end of those 10 steps, you've got a completely built engine, and you're going to have the confidence that when it comes time to start it for the first time, it's going to produce great power, great torque, and most importantly, it's going to deliver great reliability. The course is generic, so it doesn't matter whether you're building an inline 4-cylinder or a V12. Maybe it's naturally aspirated, turbocharged, supercharged. The 10-step process still 100% applicable. Within this course, we also include a library of worked examples where you can watch the HPA 10-step process being applied on a real-life engine building job. In that library, we vary the type of engine we're working on so that you're going to get experience on a wide range of different platforms. And relevant to today's interview, we will be adding a worked example very shortly on our own Honda K20 naturally aspirated endurance car build. Moving on, we're also including in this package our How to Degree a Camshaft course, and upgrading the cam or camshafts is probably one of the most common ways of getting more power with a performance engine build, but degreeing or dialing in that cam correctly to the manufacturer's specifications is critical if you want to get the performance that the cam has to offer, as well as making sure you avoid expensive failures such as valve to piston or valve to valve contact. This course also includes a simple 6-step process you can apply regardless whether you're degreeing a cam on a simple pushrod engine or maybe quad cams on a V12, it doesn't matter. The 6-step process is 100% applicable. We're also including 2 full years of gold membership, which gives you access to our private members only forum. This is the best place to get reliable answers to your specific engine building questions. And that gold membership also gives you access to our regular weekly members webinars. These webinars are a live lesson that we hold every week. We vary the topics between engine building, engine tuning, wiring, 3D modeling and CAD, just to name a few. If you can watch live, you can ask questions and get answers in real time, but if the time zones don't work for you, as a gold member, you can review our webinars in our archive, where we've got around 350 hours of content. This is an absolute goldmine, one of the quickest ways to expand your knowledge on a huge range of performance automotive topics. So remember, that package is normally $299 US. Use that coupon code Bourne HPP 100, get $100 off. You are still protected with our 60-day no questions asked money back guarantee. So if you purchase and for any reason at all decide it's not quite what you expected, let us know. You'll get a full refund of the purchase price. Let's get back to our interview with Terry now. All right, let's move on and get into this Honda K20. I mean, yeah, no secret, it is what I'd consider arguably, or maybe unarguably, the best 2-litre 4-cylinder naturally aspirated engine out there. I don't know if anyone could come up with something better, but if it's not at the top, it's very, very close too. What is it about the K20 that makes it so good? Because, I mean, in this day and age, it's actually a reasonably dated engine, at least the earlier port-injected, K20. It's an older design now.
Yeah, no, I mean, it's just fundamentally good in every area. I mean, one of the big reliability aspects, I suppose, is having a chain drive over a conventional. A lot of full 2-litre engines have a cam belt. I think there's a lot of, especially when you're taking the engine and putting it on the paddle shift, the rate of acceleration of rev change is so high. It's not really something that you always want to be running a cam belt with, but to have a chain is, effectively the perfect setup is to go gear drive, but from a cam belt to gear drive, there's chain drive in the middle. And I think when I've been using the engine in V2V and endurance racing, that chain drive has been one of the big aspects for reliability. But yeah, also rate of acceleration of revs of the engine, it just XXL out the box is crazy. Anyone that's ever driven one will know. Obviously they got the mathematics right with the B series engine, and that had great XL of revs. But I think it's not just the power that the engine makes, the way that it has been designed on airflow and like engine design to create that XL is mega, and it's something that you only really normally see in top level designed from blank sheet engines to have that rate of acceleration of revs. And I think this is something that a lot of people miss, is a lot of people are just chasing power numbers, but actually engine speed and rate of XL is also something that gives you a lot of on-track performance, which is why when we've gone to design our own turbocharged version of the K20, we've gone to a 2.2 instead of a 2.4, because a 2.4 would offer you more power and torque, but actually your piston speed declines massively when you go to a 2.4. So what we've found is with the 2.2, we've gained power and torque, but we haven't lost the piston and crank speed, which is actually mega on corner exit. And obviously, when you're running an aero car like we are with Suki, our time attack car, trying to get to maximum downforce speed, generally with that car, it's about 150 mile an hour. We want to get to 150 mile an hour as fast as we can. Then we hit the rear wing of maximum downforce, and you really need like a lot more, 250 horsepower more to punch through the maximum downforce. So having that rate of acceleration of revs in what a lot of people call the line under the curve, to try and have that from corner exit to your maximum downforce point and get the car accelerated as fast as you can, is really the key to on-track performance. And obviously the Honda bodes itself well for that. So
okay, just coming back to the sort of rate of acceleration of the engine, I mean, this is again an area that most people would give no consideration to. And I mean, in simple terms, I would say a good example of what you're talking about here is maybe if you manage to remove weight from your flywheel, which is pretty easy to do if you're starting with a production engine. you're not going to measure the improvement in engine performance from that lightweight flywheel on a dyno. It's still going to produce the same power and torque, but it's sort of almost no different to removing mass from any other part of the car. It's actually going to allow the car to accelerate out on the track quicker. So again, what you're saying, they're getting up to that Vmax 150 mile an hour where you're basically hitting an aerodynamic wall quicker. Is that a good analogy there?
No, perfect. Yeah, like a lot of engine design and tuning nowadays, people forget about the weight, and I think that was probably something that they focused more on in the older days when they didn't have accurate dynos like we do now. A lot more emphasis was put into lightweight cranks and lightweight components, and what we see in some of the aftermarket now is there's quite a lot of, we strip engines, there's quite a lot of bulky bits and heavy bits, and obviously when we went to design all of our own internals for our 2.2 turbo, a lot of emphasis was put on the lightness and strength, trying to retain the strength in the design, but trying to keep all the components as light as we can and trying to gain as many wins as we can on engine excel.
Yeah. All right. I want to just come back to another element you talked about there, which is the chain drive. It's pretty common on production engines these days, obviously, in terms of a factory engine, low to no maintenance compared to a cam belt, which is great for the end user. I'm just interested, though, you mentioned about gear drive, which is, as I understand it, a reasonably common approach on all-out competition engines. Where's the downside with gear drive? Why is it not being used in a production engine?
It's just very expensive, and also most of the race engines at that level that I've worked on only have a 6,000 kilometre life, which is, the distance of Le Mans. Built into the regulations of F1, an engine life is 6,000 kilometres, so they do take a lot of servicing. There's bearings inside the gears and there's a lot of lubrication. It's just a much bigger technical move to get to a gear driven engine, and a lot more servicing required. Effective. It's not really something that you would ever see in a road car. Okay,
fair enough. The advantage of that is this just in absolute accuracy of cam phasing with crankshaft position?
Yeah, I mean, obviously there's other benefits that you can incorporate a K in easily, but when you've got that amount of power going through the drivetrain, gears are generally the most robust and reliable way to do it. And like we touched on, like a lot of high level engines have such high speed of excel that sometimes a chain generally isn't going to be or stand up to the pressure that it's going to see. So yeah, that change in speed, especially when you're going, you're braking into a corner, you're buzzing down the gearbox and a sequential gearbox, the rate of acceleration of change there, you really need a heavy gear set in the gear train on the engine for reliability, effectively.
Okay. All right. So we've talked about the fact that the K20 is a great engine off the showroom floor. Where are its weaknesses? Where are the problem areas that kind of need to be developed out of it when you're turning it into a race engine?
So one of the big aspects is obviously oil delivery to all of the components, and one of the first things that we do is go to a dry sump setup. The bearing clearances that you end up running the K20 are very crucial, and they literally don't like running without any oil pressure. As soon as they're anywhere below sort of 3.5 bar, we've seen issues. So as soon as you're incorporating a lot of G into a car, especially with our time attack car, we're on slicks with twice the amount of downforce as an F1 car has. So the Gs that we're seeing are very high, and the amount of oil swash in the wet sump is just far too much for the pickup pipe, and we've had to go to a dry sump setup. So that's one of the key things for reliability, I think, is getting your oil system right. And also getting into oils too.
I can understand at the sort of time attack, high downforce level, the dry sump, obviously it sort of becomes a non-negotiable. And while they are expensive, if it saves you an engine, all of a sudden it looks like a pretty cheap investment. However, I mean, if we take it back a notch, and maybe it's just a little outside of the realm of the level you are working at, there are a number of solutions for, weld-in or bolt-in baffle boxes and sort of trays, etc., that go into the factory sump. And I mean, I've had personal experience with these at club level, and they do seem effective. Is there a point where these are an okay solution? And if so, at what point do you consider the dry sump as the only way to go?
Yeah, effectively, we've had quite a lot of experience, and there is some good baffles out on the market. And for a lot of tin top racing, that will be absolutely perfect. I think Skunk 2 do a baffle. There's a few different companies that have produced the baffles, and they work really well. Work really well at just keeping the oil around that pickup pipe and not letting it move to all sides of the sump. I think the big thing on a K20 is when you're entering a corner with heavy braking, quite a lot of oil can disappear up the front timing chest because there's the gap there. So I think having a decent baffle, but there's some other bits and pieces we've made some little plates up on some engine specs that we've done to just stop the engine from disappearing up that front timing chest. I think that's another key feature, really. So
okay. In terms of the lubrication benefits, that's pretty understandable with the dry sump system. I'm interested to sort of get an insight into, do you see a power gain with a properly designed dry sump system? And again, this is easy to overlook, but one of the benefits is that we're removing those blow-by gases, evacuating the crankcase of blow-by gases, which includes oil droplets as well. So this reduces, therefore, the windage losses in the crankcase, which is basically the conrods and the crankshaft counterweights having to sort of break through this oil mist. So there can be some benefits there. Also, the fact that you can run a vacuum in the crankcase if it's sealed can improve ring seal. So yeah, can you give us some understanding of how you see that working?
Yeah, so we haven't really seen benefits on the K20 yet, but like a lot of the blank sheet engines that I've worked on, we have very efficient scavenge pump system. So as soon as you said, you can get the crankcase pressure into a negative, you do start to see big horsepower gains. But I'd say the general kits that are out on the market for the Honda K20, it's very difficult to get the crankcase pressure below atmosphere, really. So really, it's more of a reliability thing from what we've found so far, and we haven't seen pumps on the general market that are that efficient that can start to pull a negative crankcase and relieve pressure from the bottom of the piston. So yeah, we've just gone with a lot of stuff that we've done to a dry sump system. One, for packaging, it obviously helps. The standard Honda sump is quite deep, so we've done a lot of installations on. We're working with a company at the moment called MK Cars that produce a sort of Sevens lookalike car, a kit car that you can buy and assemble in your garage. But for that application, trying to limit the sump to get the ride height back on the car has been a big movement, really. But yeah, I think there's not too much power gain from what we've seen. It's just a reliability and a packaging point of view with a dry sump setup.
Well, I must admit, that's not what I wanted you to say. We've got a daily engineering dry sump system going on our new K20, and I was hoping that we might see some benefit from it. It may still pan out that we actually get to do a back-to-back between wet sump and dry sump, which obviously will put that argument to rest, at least for that particular engine. And as you mentioned, for those who maybe haven't sort of had intimate knowledge of the K20, it is actually quite a tall engine, so that can provide some packaging issues. Case in point is we have one in an EF chassis CRX, and it's a big engine for a little chassis. So the other benefit of going to the dry sump is it's going to reduce the overall height of the engine for us, making packaging a little bit easier. Coming to the piston design, there's always a bit of a sort of a balancing act when it comes to choosing a compression ratio, and the octane of the fuel available is obviously one of the driving factors there. What have you sort of settled on as a compression ratio target for naturally aspirated applications?
So yeah, a lot of our crate Honda K20 engines are obviously designed to do 2 seasons of running on UK pump fuel. So what we've found is that we can't go anywhere above 12.5 to 1 compression ratio. So yeah, just pre-ignition and detonation creep in when you start to raise the compression ratio above that. So using that as a limiting factor to produce more power out of the 2-litre engine, we've really dialed in on the bit that we can change, which is obviously cam profile. When we've spent a lot of time developing cams for the Honda K20, we sell a high lift cam on our website, and one of the aspects of going to that high lift cam is to get rid of the V-TEC also. So we've sort of limited a lot of clubman level motorsport in the UK and Europe, we're limited to 99 RON octane out of the pump, and really your compression ratio is dictated by which fuel you can run on. So
yeah, absolutely. I'm just interested on a tangent there. If you were not limited on octane, and maybe you had the benefit of like a proper race fuel or alcohol-based fuel, where would you then go to with compression ratio? And do you kind of get into this area of diminishing returns? Obviously, as we build up the dome on the piston to increase the compression ratio, we sort of start interrupting or potentially interrupting the flame front propagation during combustion as well. So at least, again, as I understand it, we can sort of get into this area where we add compression ratio, which should be a benefit, but we're actually compromising the combustion event and therefore kind of going around in circles and making no gains.
Yeah, and I think the other big thing is not to focus on the compression ratio, but to come back to the overview again and focus on the airflow. If you keep building so with a naturally aspirated piston, I would call that piston shape a penthouse. So we have that sort of domed penthouse shape. And a lot of the design of that in the early stages was to increase the air speed across the top of the piston. So that shape sort of pushes the air to the top of the combustion chamber in the head, and as you force the air into a smaller gap, you increase the air speed. So this comes back to having the sensors either end of the engine. Like, you might just see some small gains by keep increasing the compression ratio, but then you might start to lose air speed across the top of the piston. So I think this is where, when you don't have all of this sensor set up around an engine, you could get a little bit lost effectively, and you're chasing or maybe going down the wrong avenue. And I think the big thing in engineering that I've learned over the years is not to ever get lost down an avenue. Keep coming back to the overview and looking at the broad spectrum of what you're trying to achieve and where you're at with other aspects. And chasing compression ratio, in my experience, is not really the way to always make the power and build an efficient engine. So
summing up, if you were not octane limited, am I getting the sense that you wouldn't really be putting a lot, if any, more compression into these engines?
I think if I wasn't octane limited, we'd probably end up at around 13.5 or 13.8 to 1. From other engines that I've run, NA engines that I've run on nice fuels, that's sort of where we've ended up. But obviously the real trick to all of this is your compression ratio is one aspect. Actual piston shape to increase the air speed is the aspect that a lot of people don't really focus on. And that air speed is the bit that gains the power.
Fair. Again, we've kind of already mentioned this, but yeah, can't look at one element in isolation. It's the entire package that counts. All right, coming back to, you were talking before about cam development and particularly developing this high lift cam that eliminates the V-TEC. I mean, I'm guessing that there's probably no one listening to this podcast that doesn't understand V-TEC, but just to be super clear, Honda kind of, at least I think, pioneered this, and have two different lobes on the camshaft. A smaller lobe that's used at idle and low RPM, which is uses little lift and limited overlap for good efficiency, nice road manners, good economy. And then at higher RPM, they switch to a larger lobe with more lift and more duration, more overlap, that benefits high RPM performance. So on face value, I would think that's kind of the best of both worlds, compared to a conventional race engine where we're one fixed cam profile. We're going to make some compromises at some point in the rev range, so we've got gains in others. Why go away from that V-TEC mechanism on that basis?
Obviously, a lot of the engines that we've gone away from that on are full-blown race cars, and we're in control of gear ratio. So this is the other aspect. You can never just get stuck as an engine man here. You've got to look at the whole drivetrain package. When you're in control of gear ratios, effectively you are going to lose power and torque at the low end, going to a fixed gear and cam. But once you're in control of the ratios, the engine never sits there. You're never operating in that part where you've had a loss. You're only ever operating in the window that you've had a gain. And what we've found we have a pin that locks the V-TEC out. We've gone to a fixed gear and our high lift cam, and that has jumped power and torque up massively from 4,500 RPM onwards. Generally on track on a lot of race cars where the gear ratios are changed per track setup, we would never see anything less than 5,500 RPM on circuit. So
essentially you're never in a position where you would have benefited from that low lift cam profile anyway.
Yeah, and then coming back to the efficiency that we've built into the Honda, all of the bits that I've learned through my career on vibration, where we're not making the power and torque and we're never in that, we've designed crankshafts and camshafts that all of their critical speed is around the 3,500 RPM mark. And literally the only time our race engines see that is when they're leaving the pit lane or pulling away from the box. So, everything is designed to be between 5,500 and 9,500.
Okay. Yeah, that makes a lot of sense. I'm guessing there's a potential reliability gain as well in removing or eliminating that V-TEC mechanism, just one less thing to mechanically fail or go wrong.
Yeah, there is. But I suppose coming back from the race engine world, we've also developed parts for the fast road car world, and we developed an engine package for the MK, which I touched on earlier, which is like a sevens based car. And for that package, really, you want that full spectrum. You want that low drivability. You want the power when you need it. And actually, the V-TEC system has been mega in that car package. The car only weighs 600 kilos. So, we don't need the last tenth of horsepower. It's just not needed. But to create a very nice drivable package, the V-TEC we've retained, and we've developed our own drop-in to keep the V-TEC system. And that's performed well. We're seeing over 250 horsepower now on the drop-in with the right manifold and exhaust system. And in a lot of applications, you don't need it much more than 250 horsepower. That, combined with the rate of acceleration of revs that you see in a Honda, even as a track car, they still outperform quite a lot of other track cars that are your general use. Like, there's a lot of Ford stuff running about in the UK, a lot of people into Pintos and bits and pieces like that, and it's just a whole different world what you can do with a K20 compared to what you used to be able to do with a 2-litre Pinto.
Yeah, I mean, absolutely. I remember when I was just getting involved in the industry back many more years ago than I care to mention, and the magic number always used to be for naturally aspirated engines that were fairly heavily developed, sort of 100 horsepower per litre. That was good. I mean, if you were north of that, you were doing pretty well, and now we've got a production engine that essentially with a tune, I sort of just looked at some of my numbers, and with a stock K20 with a air filter, a headers and an exhaust system and a reflash, a tune using maybe Honda, 220 odd horsepower at the wheels is pretty easily achievable. So it's amazing how far technology has come. Go back to the old Ford Pinto engine, you're going to be struggling to sort of trump a well-developed K20, aren't you?
Yeah, no, and I think the other bit that Honda got so right is they understood the airflow when they come to design this production engine. It's very difficult with an NA with the right compression ratio to the fuel to mistune and to run into detonation. Where they've got the airflow so right, the engine characteristic is that it just rolls over. So actually, for a lot of people that have taken your courses and are getting into tuning, I would always urge them to go and map a Honda, because it's the airflow so good. You can get away with being even 3-4 degrees. You'll just literally see the power drop, but you won't break the engine. And I think coming back to this clubman level, what it needed was this very reliable high output power engine, and that Honda K20 ticks all of them boxes. It's very difficult in my experience to break it, and that is obviously the core aspect of what makes a good clubman level engine.
I mean, challenge accepted by many tuners out there. Any engine can be broken if you try hard enough. But I would agree they are a fairly easy to tune engine, albeit, in stock form, there's a few things going on with the cam control and the V-TEC mechanism. But, you can be a little out of the window and they're not going to immediately sort of bite you. It's a good engine to learn on, particularly because it does have those more advanced elements. Now, we've already talked about the fact in your race engines, you're deleting the V-TEC. You also alluded to the fact you're using fixed cam timing instead of the iV-TEC or cam control. In stock form, that gives you 50 degrees of cam movement. And again, at a real quick high-level overview, we could advance and retard the cam timing manually using vernier cam gears, but that's fixed. Once we've selected a cam timing, we can't change that on the fly, and there's normally some compromise that comes into that, whether we want to focus on improving lower RPM performance or higher RPM performance. With continuously variable cam control, we can advance and retard the cam timing as the engine's actually operating, kind of getting the best of both worlds. Now, obviously, as we go larger in the cam profile and there's physically just less room to swing that cam, you're going to run into problems with contact. Is that why you've eliminated the V-TEC, the cam control mechanism? Or again, does it come back to that you're just operating it over a relatively narrow RPM range, so the benefit in low RPM performance is kind of really irrelevant at that stage?
Yeah, exactly that. And once you go to that fixed gear, I think coming back to the overview and not going into one component, coming back to the airflow, we're just trying to, in that small rev range from 5.5 to 9,500, we're trying to create not just the best airflow through the engine, but we're also trying to create scavenging from the exhaust system. So you get to a point with a straight 4 engine that you get what's called a secondary pulse. And if you've not understood the whole overview of the airflow, you can actually end up with a lot of back pressure back on the exhaust valve, killing power. And obviously the perfect place to get to, so we end up stepping exhaust. So we would have 2 or 3 steps in the exhaust system, getting the inlet track length right. And in the cam profile, you need to get all of them aspects right. And then once that's all perfect, you can actually get into what we call scavenging, where you've lost the secondary pulse and the engine is actually scavenging out and you've got the pressure going one way through the exhaust system. As soon as you can get to this point with a K20, the power benefit is massive.
So that secondary pulse you're talking about there, if you've got that occurring, I'd be right in saying you're essentially diluting the fresh intake charge during the overlap period because it's drawing exhaust gas back into the cylinder, basically offsetting some of the volume that's available for fresh air and fuel to be ingested.
Yeah, exactly that. And like a lot of this fine level tuning work will also be done track to track. If we're going to Brands Hatch, for instance, we would have a whole different engine configuration on an NA to what we would have at, say, Silverstone, or a much longer track. And that's a lot of the work that when I first got into F1, we were still running the naturally aspirated V8. And there was a lot of work done before every Grand Prix on developing the package for that track and the conditions that it was going to see. So obviously, when we're dealing with the aftermarket and the clubman, there's not so much room to be changing inlet track length and exhaust length all the time. But one thing with our partners at AT Power, they've developed individual throttle body setup for the K20, and it's got a interchangeable center section, so you can actually change your inlet track length. And if you want to get to that, and I'm sure as we go through the next 20 years, I think we're going to carry on racing K20s, and generally what happens in history of engines is more money gets spent every year you go racing and the development becomes higher and higher. So bringing that experience that I had from the NA days of F1 when I first started back into the Honda, and having that ability to change the inlet track length and the exhaust length and sort of produce a setup for the circuit that we're going to is really it. Obviously, we've sort of found a sweet spot now. We've sort of got a out-the-box setup which will generally work at a lot of circuits. You would just change your gear ratios to that circuit. But if you want to get into the last tenths of it, there is always gains to be had from changing from a sort of a low speed circuit to a high speed circuit, and the engine configuration changes.
Yeah, that makes sense. There's no one size fits all solution here if you want the ultimate performance. Since you've just touched on inlet designs, let's just talk about the individual throttle body style inlet versus a conventional factory style plenum inlet. Where are the pros and cons of each? I think most people kind of just assume that bolting on a set of ITBs is instant power. Is that always the case?
No, I think a lot of it comes down to packaging. There is, with the K20, a small advantage from going to a individual throttle body, But the big advantage that I found from going to an individual throttle body is being able to run stage injection. We've built a couple of engines now where we've had 2 injectors per cylinder. And coming back to that engine efficiency that we was talking about, your atomization of your fuel is much better at high RPM when you can inject the fuel a lot later or a lot further down the inlet track. It just mixes with the air and you get a much better burn. So the high-end engines that we've done, we've found a small gain going to an individual throttle body, but then we've made that gain amplified by running split injection. And generally we would run the primary injector up to about 3,500. And in the life racing, so we was getting back to managements and that, every management will pretty much get you MBT or peak power. But then these little strategies within the life racing allow you to phase the 2 injectors one over the other. So when the engine's flat out at like 9,500, we've actually found that a 70-30 split. So we've got the outer injector running 70% duty and the inner injector running 30% duty. That's where we've picked up more power, but there's still more work to be done for us there. We've only really produced 3 engines to that level so far.
Yeah. I'm interested, and this is again from a purely selfish standpoint, because we're doing exactly the same, aiming to run a set of secondary injectors outside of the inlet trumpet. So not to put too fine a point on it, how much more power can I expect from doing so, and then optimizing the staging? As you mentioned there, you found 70-30 worked well. Yeah, are we talking 1 or 2 horsepower? Are we talking 5 or 6 horsepower?
So on a 2-litre race engine, I think we found around 16 horsepower from getting the inlet track and the stage injection. And obviously the big bit is I've seen a lot of people put individual throttle bodies on engines, and then they'll go and put the engine into an EP3, and then they end up with a tiny little airbox. So a lot of it comes down to packaging. And all right, it's all right having the stage injection, but you need to be able to get an airbox scoop into that to actually see the benefits from it. And if you go back to British touring cars when they were running DC5s, so to get our airbox shape, we looked at some of the work that Neil Brown had done in British touring car and the Super 2 2000s back in the day. And we've sort of created an airbox for the DC5 application that takes the air from on top of the rad. We've put some heat proofing underneath so you're not getting that heat from the rad into the airbox. And then just having a nice package and not trying to restrict the front of the throttle body is obviously key. I always call it the bank of air, but effectively I feel the bigger airbox that you can get generally is the best, and trying to get an airbox to incorporate a panel filter is the most efficient way. Air flows through, from what we've found, air flows through a panel filter much more efficiently than a cone filter. And you've got a much bigger surface area, so trying to get a big airbox with a big surface area to incorporate a panel filter is the key to unlocking the individual throttle body in a Honda, and that's when you start to see the gains.
Yeah, that makes a lot of sense. And I mean, again, it's kind of looking at the whole installation now. We're sort of looking even broader than just the engine. There's no point having this ultimate inlet set up with the right length trumpets, ITBs, etc., and then having those ITBs jammed up hard against the back of a radiator, pulling in hot air. Obviously that just doesn't make sense on any level. When it comes to choosing individual throttle bodies, not necessary just for a K-series engine, this can be confusing. And again, we've just kind of gone through this process ourselves. There's a variety of different diameter throttle bodies available. Is this a case of just literally bigger is better, or how do you size this? Is there some math that you can do to find out what's going to be suitable, or is it unfortunately an expensive case of trial and error, testing back to back on a dyno and literally just seeing how the engine responds?
Yeah, I mean, what we've found since developing the Honda is a lot of people have got caught up in bigger is better. And coming back to the overview of airflow and airspeed, when you're developing a high power 2-litre NA engine, you want the airspeed through the engine and airflow to be as efficient as you possibly can. And actually going to a bigger port sometimes loses you velocity and airspeed. So it looks like, to the visual eye, having a big port and a big throttle body is going to gain me more power. but actually you end up losing your speed and your velocity and your power will go down. So yeah, there is a little sweet spot. I know I wasn't allowed to say a lot of bits about my earlier career, but that's one little sweet spot that I'll keep to myself at the moment, just for our engines. But there is a sweet spot on throttle body sizing and head porting. So one massive gain that we've found for airflow across the K20 head is to go to a 1mm oversized valve on inlet and exhaust. And if you haven't got massive budget, you can actually go to a decent machine shop and have the standard seat cut 1mm oversized. So, generally when you rebuild an engine, you're going to have the seat cut anyway. So we've done a range of valves that we now sell on the Bourne HPP website as well. And we've done a 1mm oversized inlet and exhaust that you can buy straight off the site, but there is massive gains. The big gain really is if you're going to run an NA application, I would say on an overview, don't go too big on port size. Bigger isn't better, but actually trying to having a 1mm oversized valve, we have picked up the gain. So yeah, there is a gain there.
Again, could you maybe put some numbers around what that 1mm valve size increase is worth?
So on our sort of Clubman level 2 litre engine at sort of 12.5:1 compression ratio, 1mm oversized valve, individual throttle bodies, we've seen over 300 horsepower on pump fuel. I think there's around like an 8 horsepower gain from going to the 1mm oversized valve.
Yeah, it's not insignificant.
It's always that last 10 horsepower. We were stuck at around 290 or 99 run for ages. And then the big bit that opened up that last 10 horsepower to get past the 300 horsepower stage is all down to exhaust track length and scavenging. And once we cracked the scavenging of that airflow across, that's when we started to see that last bit of gain. But unfortunately, that last 10 horsepower is always the most expensive. I think if you was to take a crate engine, or if you took an FD2, so if you took the Japanese spec FD2 spec engine, or they call it the JDM spec, that's got 12.5:1 compression ratio from stock. If you was to just put a high lift cam, fixed gears and 1mm oversized valves, you could expect to see sort of 280, 285 on 98 run. So that's really the engine package that we've sort of pushed because it's the most power for buck effectively.
Yeah. People listening who are maybe more familiar with turbocharged engines will be thinking about the numbers that we're talking about here, maybe shaking their heads and thinking, what are we even talking about? I think that is why naturally aspirated engine development is so satisfying when you get it right, maybe frustrating when you're not quite in the ballpark, is because you are talking about a lot of work for relatively small gains in power. We don't have the benefit with a naturally aspirated engine of just turning the boost up another 1 psi and making 20 or 30 more horsepower. It's just not that easy, but again comes back to just making sure that every single component in the engine is working in harmony with the others. Just following on from the valve size discussion, the port shape or the head flow for the K20 I think is probably one of the elements that makes it such a successful engine. I mean, it's just so good in stock form. Is it an area where there's some good low-hanging fruit, getting a quality port profile put onto that cylinder head, or is it also really easy to actually make it worse?
So the biggest gain that we've seen on an A spec and also a track spec engine is really opening the throats up. So the area of the cylinder head just in front of the valve, you can find some big gains with porting that. We haven't, because we're trying to keep the airspeed up on the NA setup, we haven't really found massive gains with opening the stock port up too much. We've obviously developed the throat shape and then blended the port out from the throat shape. And obviously going to that 1mm valve, we're sort of taking around 1 mil out of that area around the valve to unlock the potential and surface of that valve. But yeah, so the work that we've done so far, we haven't even got to the CNC porting stage, to be fair. Everything that we've done at Bourne on our big power engines has all been hand ported because we're not taking too much out, because what we found is that the stock port size is just so good, and we've found other benefits in getting, as we touched on, inlet track length, cam profile and exhaust length as a package to work. And in the big bit, has been the scavenging of the engine. I think a lot of people have maybe got a little bit lost down the rabbit hole of the port inside to produce power from these engines, but we've found it in other areas, and it's been more efficient in other areas as well. So
makes a lot of sense. I think we've kind of done the NA route to death, but I mean, you're not just involved in naturally aspirated engines, and you've developed a turbocharged 2.2 K series for an NSX time attack car, which kind of I've alluded to already. What are the challenges when you want to take this really good factory K20 engine, and instead of making 300 horsepower aspirated, you want to maybe make 700, 800, 900, 1,000 horsepower with a turbo on it? Where are the new sort of weaknesses that creep in?
So one of the first parts to go to was obviously when you're going to target 250 horsepower per cylinder, the actual stresses that the components are going to see. Forget chasing airflow and power, just the physical design of components needs to be so robust. So one of the key factors in the K22 that we designed is we went to an 89mm stroke crank, 92mm stroke crank, but we managed to drop the rod length by 3mm. And what that done is open up a lot more room in the piston crown. So what we've found on a lot of turbocharged engines that I've worked on through the career is having a much thicker crown obviously helps you to dissipate the heat and sort of gives a lot more strength to the piston. So we worked with the masters of piston design in Germany, which is a company called Pankel, and they used a supercomputer to design the underneath of the piston for this engine. So it's not really even something that could be designed by the human eye. It's been developed for a stress point of view.
This is sounding like an incredibly cheap process already.
No, it wasn't really the cheapest way to go, but to try and do what we wanted to do. I think the other bit, people will probably question why we went to that extreme. But I think what we've sort of found since coming into the Honda market is a lot of products that are out there are all designed to do quarter of a mile sprints. And effectively, you're only doing 5 gear changes. You've got 5 on-load points. Whereas when we're doing time attack, where we've got an hour's run in a day and 1 lap of Brands Hatch, we might see 50 gear changes, so, it's the equivalent to 10 quarter mile pulls on 1 lap. So I think the engineering that had to go into just making this 1,000 horsepower robust for track laps or track use is just a whole different engineering principle or level, to be fair, than just developing it for the quarter mile. I think also in the UK, we sort of expect a time attack engine running 1,000 horsepower to complete a whole season, which could be up to sort of 80 hours of full chat running. Whereas I think a lot of customers in America with their quarter mile, I don't know exactly the life that they'd get out, but I think a lot of people are seeing, if they do 2 or 3 runs on one engine, that's a good engine. So
I mean, if I take it back to my my 4G63 drag racing days, I mean, at one point we did improve reliability and we weren't seeing failures, but I mean, that engine was getting stripped and inspected and freshened up probably after 10 passes. So what's that? 4 kilometres of race use. It's not a very economical process. I've always said that it is harder though to make less power for an endurance race application than it is to make insane levels of power for 6, 7, 8 seconds in a row for drag racing. Just the amount of time the engine is under stress. It's just chalk and cheese, absolutely completely different. I can't help but wonder where you saw the shortcomings though in the off-the-shelf components. I mean, these days making 1,000 horsepower in a K20, there's, I'm not going to say it's easy, but there's a pretty well-trodden path to getting there. And there's off-the-shelf pistons, conrods, crankshafts from a number of companies that have been proven at that point. Is it just come back down to, again, that sort of confidence that not only will it make 1,000 horsepower for one race meeting, but it will actually do a season of time attack?
There is that, but I think when you're running a time attack car and you've got no limit on power and regulations, you've also got no limit on aero. And Suki, which is Tegua's time attack car, well, I think we're close to 2 times the amount of downforce that a current F1 car can produce. So the point that you actually get to maximum downforce, the actual, and one of these areas that people maybe mind doesn't go to straight away, which we see day in, day out on engine dynos, is load. And the amount of load that engine is under. We've got 4 pistons with 250 horsepower of cylinder pressure on top of each one, literally hitting a brick wall of load when they come onto maximum downforce. And that just creates a whole level of load on these components. A lot of sort of 1,000 horsepower, I mean, the number gets bandied about quite a lot. It's not really in a lot of sort of applications or cars that engine has come out of, DC5s or EP3s. Generally, I think they have a dyno queen 1,000 horsepower, and what actually gets run in the car is something different. But then on a lot of tin top applications that may have 800 horsepower, they're not fighting this wall of load with the aero. Generally, they'll have a small amount of aero on some of the DC5s that I've seen in Time Attack, but hitting this wall of aero just comes, the actual components that we've needed have just needed to be another level in durability effectively to suffer that life. So
yeah, that makes sense. I should have mentioned earlier as well, for those who haven't heard the name Pankel, I mean, it's not one that we see much in the enthusiast level market, but Pankel are well known for manufacturing components at the F1 level. So, this is a company that absolutely knows what they're up to. The other aspect I wanted to dive into is you mentioned that you went to a stroker crankshaft stock form there in 86mm stroke, 86mm bore, what we call a square engine. You've gone to a 92mm stroke to get to that 2.2 litre. Conventionally, the problem we have here, I mean, it may not be a problem, but the knock-on effect of this is reduces our rod-to-stroke ratio, which is simply the ratio between the stroke and the length of the conrod centre to centre. You mentioned you went shorter on the conrod, I think you said by 3mm, in order to facilitate that thicker crown, where conventionally with a lot of these stroker engines, we actually see that they retain, obviously geometry notwithstanding, the stock length connecting rod, and then to get the compression height back to where it needs to be, they move the wrist pin higher in the piston. So the benefit there is the rod-to-stroke ratio with a stroker engine would be superior to shortening the connecting rod. Admittedly, 3mm, it's not a massive amount, but you obviously saw the need for, or you prioritised that thicker crown over the rod-to-stroke ratio?
Yeah, so like I was explaining, in my earlier career, I've always done a V1 and a V2. So we made a V1 engine out of slightly cheaper components, and that retained the stock rod length. And what we saw trying to run up to these powers and, hitting the load sites that we're hitting with the aero, is that the cylinder pressure was becoming so high that we was actually cracking pistons. We was cracking through the inlet port, and a lot of that some of it was to do with the physical pressure on top of the piston, and also some of that was to do with our heat rejection. Obviously, having more material there allows the heat to dissipate quickly through the piston and ultimately into the cylinder and into the cooling jacket. And effectively, the more material that you can get in there and dissipate that heat as fast as you can, the more durable it's going to become. So there is I won't tell you the number, but there's a size that a rule of thumb that I've always gone to on piston crown thickness to try and get back to that durability. So it's one of them. Unfortunately, with all the best supercomputers in the world, there's always been a bit of real life experience built back into that. And like a surgeon now, I've done it that many times, you sort of just know where to cut now. So a lot of it is done without thinking nowadays with what we go to on piston crown thickness, and it's just a given. But yeah,
I mean, speaking of not thinking, this is an element that most in the enthusiast market wouldn't ever consider, because we don't get to choose the thickness of the piston crown. It's whatever came in the box of shelf stock pistons that we just ordered from JE or Wiseco or CP or whoever it may be. So that's quite interesting. I did have this issue earlier on in my development of my 4G63 drag engines. Obviously at that point we're using a bespoke piston to my own design because nothing off the shelf was really up to the task, and we did see some piston cracking fairly early on, and we actually improved the reliability there by increasing the thickness of the piston crown, albeit I always stayed at 2 litre for my drag engine, so we weren't sort of balancing that sort of rod to stroke ratio with a stroker crankshaft. We had the flexibility to do that, but So that overnight fixed most of the problems we're seeing with that. Another element with the K20 is the sleeve design, the way it's sort of an open deck design, if you like. Not really an issue necessarily, I guess, with naturally aspirated engines, but as the cylinder pressure climbs with turbocharged applications, we can see problems with head gasket integrity with these liners moving around, ultimately cracking. At what point do you need to consider moving to a ductile iron sleeve or something like that?
I would say if you're, even with an NA application, if your budget extends to it, I would run a dart and liner or a sleeve block, mainly because even with the NA stuff, on a lap, the boreability of a standard bore, or the movement on a lap from the heat around it, you're constantly giving away power. Like, it's not a gaugeable thing, and there's not really a lot, even with great crankcase pressure sensing, you're not generally going to see it. But just from what we've seen in the past with standard bores, your OE piston is constantly moving, your bore's constantly moving, and there's 2% of gas loss that side, then the actual cooling around the water jacket is not consistent. So, your water temperature goes up and down, heat, especially on heat soak. So when you stop at the edge of the box and the heat soaks from every other component back, you might then fire up and your bore's moved in this position and you've lost a tiny bit here and there. So trying to limit bore ovality and bore movement is obviously, on a performance engine, even NA spec, something that I would try and do early on in the build. So
yeah, that makes sense. Yeah, again, I think most people assume that the bore stays round, and it obviously doesn't. It's going to move with cylinder pressure. Obviously, that's amplified with the sort of cylinder pressures we see in a turbocharged application, but still in a naturally aspirated application, it is going to happen. And really, we want to try and retain that perfectly round bore, because that's going to help improve our ring seal, and that in turn is going to account for an improvement in our power.
So just to jump in there, I think the other bit that people forget about is the sort of silicon content that is in a lot of aluminiums as well. And you might go and have 4 OE blocks, and the actual gap between the room in between the actual aluminium particles, that the purity of the material isn't always consistent batch after batch of engines. So to take that out, and obviously one of the first things that you do is go to a forged piston when you're building, and generally the reason that you do that is because the material quality is better but much purer. And obviously one of the big bits with an OE bore is the material quality isn't great, and the pureness of the material isn't great. So what works on one engine from 98 on the same engine in the year 2000, sometimes where they've got the material from or has changed. And just to eliminate that and get to a datum point that works, I would always suggest going to the dart and sleeve, because it is a very pure material. There's not a lot of silicons in the actual material content, and therefore your expansion rate is more consistent, and you just know where you are. So,
well, I think you should be getting commission from Darden, I reckon. That's a pretty compelling sales pitch for their product.
I'm not actually a dealer yet, so if they're listening.
Okay. I just want to talk a little bit about head gasket sealing. With obviously naturally aspirated, not usually a huge concern, pretty low cylinder pressures, relatively speaking. But as boost pressures climb, this does become a problem. At what point does the head gasket sealing become a limiting factor with the K20 design, and what are your sort of workarounds for that?
So we've found that we can run very reliably up to 1.4 bar of boost on the standard head gasket. We used some Speed Factory, I think they're 645 material head studs, and just incorporating them into the build with some ARP nuts as obviously give us a much better head clamping across the gasket. But yeah, we haven't really been able to push past 1.4 bar yet. All of the engines that I've worked on in my earlier career, I've never run a head gasket. Everything has always been a Cooper's ring or a Wells ring design, and we would O-ring the deck. So what we're trying to achieve with the Honda as we move forward in this turbocharged development is obviously to get back to or incorporate the designs that I've had in my earlier career and try and get a Wells ring and an O-ring seal in that and actually eliminate the head gasket entirely. But we're just working at Bourne HPP at the moment to try and get there. I think effectively we may end up with a wet liner, and the amount of material that's on the actual deck doesn't really lend itself to having enough room to run like an O-ring around the side of the deck. So I think I don't want to end up there, but we might end up with our own billet block design to actually get rid of the head gasket and have the room on the deck to set out the O-ring how we want to set the O-ring out to seal the water jacket. And also, if we went to our own billet block, we could actually have a little bit more room on the outside of the liner seal to incorporate the Wells ring.
It's a lot of work to go to seal the head gasket on, but at the end of the day, if you can't keep the head on the engine, nothing else really matters.
No, I think we've got all of our airflow working. I think coming back to where we've gone with the turbo, our emphasis has been on getting the airflow right on the NA, and a lot of that work that we done on the naturally aspirated engine, when we incorporated that straight into the turbo engine, the turbo engine has been really efficient straight out the box without having to run high boost levels, because our airflow has been so good and we've understood that on the NA. It's just made such an efficient engine where we're sort of close to on a hot lap, we're sort of close to the 700, 750 horsepower mark at the moment with 1.4 bar. So yeah, as soon as we can punch that boost up and have a head gasket sealing that's reliable, then I think the 1,000 horsepower number on a track lap is just going to reel itself in quite quickly.
Yeah, it doesn't sound like you're miles away. Can you just elaborate on the terminology you use there, the Cooper ring or Cooper's ring, Wills ring? What exactly do these look like to those who haven't seen or heard of these before?
So it's a small sealing ring. Normally it'll have a standoff that sits, so you would normally machine a little groove in the top of the cylinder liner, and then it's normally a white gold material with a vacuum inside it, and that sits in the groove on top of the liner, and as the cylinder head is bolted up, it actually crushes and fills the gap. And it isn't just the Wells ring that does the sealing. Normally you would have the liner set out of the bore, you would have what we call a liner standoff, and the liner's designed in a way that it works like a damper or a spring. So even though when you look at it, it's a big solid piece, it's actually designed to compress as the cylinder head's taut. And obviously then getting your liner standoff is critical, so that as the head bolts down on the head bolts and crushes the liner, all the liners are at the same height and they've crushed back to the block face. So that's been the key bit in a lot of blank sheet engines that I've worked on when we're sort of running big cylinder pressure.
These sealing rings, you said you've got a groove essentially machined around the top of the bore that they sit in. They're going to sit proud of the top of the liner, so those actually contact the cylinder head first, and then as the cylinder head's bolted down, they deform. The physics behind how these work, is this sort of a case of under the heat and pressure of combustion, they will actually sort of expand, and obviously we like to think that the head and the block are nice and rigid and aren't moving, but under high cylinder pressure that's not the case, which is why we have problems with head gasket integrity. So do these just flex enough, maybe it's a couple of thousandths of an inch, to take up any flex between the deck surface of the block and the cylinder head?
So they do move, yeah, exactly that. They do move with that, but also, as I described, the actual liner design is designed like a damper on the car, and it is only moving a thousandth of an inch and not what a damper's travelling on the car, but the actual liner is actually moving with the panting of the cylinder head. So it is quite hard to look at when you've torqued a head down to 100 Newton meters and it feels like it's going nowhere. It's quite a weird analogy to think that head is actually panting on top of the block constantly, and the cylinder pressure is so hard that it's trying to force the head away, and the head actually lifts and comes back and lifts and come back. So once you've got the right liner design, the liner's designed to move with that cylinder head. And that's where getting your liner standoff combined with the Wells ring is obviously the crucial part.
Okay. All right. I think we'll leave that there, because, again, we could probably spend another hour talking about this topic, but I think we've probably taken up just about enough of your time, and I'll move towards wrapping things up here. We've got the same 3 questions, Terry, that we ask all of our guests at the end of our podcast episodes. And the first of those is, what's next in the future for you and Bourne HPP?
So we obviously set out to develop the Honda. We've ended up getting quite a lot of intellectual property now, and not just developing the Honda, but we've sort of built our processes up at Bourne to move on. And my passion is Japanese engines, so I think we'll use the same principles that we've put together and just carry on developing Japanese engines. I think I'm 36 now. I've probably got 25 years left of my career easily. And I think moving through the years, you'll just see Bourne HPP developing Japanese engine after Japanese engine.
You've started with the bar set pretty high with the K20. What would be your next engine on the chopping block to develop?
So we've been given a 2-litre Mazda MB engine to develop for a car manufacturer, effectively. So that is actually the next engine, not by choice of ourselves, but just because that's been put in front of us as a project. But obviously one of the most efficient engines outside the Honda has always been the Evo engine. So I think possibly the Evo engine will be a market that we move into. I'm also a massive fan of the Nissan Skyline, so RB26s and bits and pieces. I'm sure you'll see some cams popping up on our website for them engines too in the future. So
okay, yeah, makes sense. I mean, definitely 2 of the more popular Japanese engines that are continuing to go from strength to strength, even sort of a long time past when they were actually offered in a production vehicle. Next question for you, Terry. Is there any advice you'd give to a younger version of yourself to help reach where you are today in your career faster? And I'm struggling to think what that advice could look like. It seems like you've really landed on your feet at each step of your career so far. But any insight?
I would say, on an overview, once you've understood the 1950s physics inside the box, constantly let your mind go outside the box and never be afraid to ask questions. There's so much engineering that hasn't been explored yet. One of my best sayings is every day's a school day. So just keep learning and keep moving forward, basically.
Yeah, I think we've sort of pounded this message in time and time again on the podcast that no one ever knows everything when it comes to engine design, engine development and calibration, and that's what keeps me passionate. There's always something, as you say, every day's a school day. You've always got something new to learn. So I think really important not to sort of put your blinkers on and kind of think that you've learned everything there is to know. There's always something around the corner. Don't be afraid to share your experiences with others in the industry. Don't lock it down and think it's all sort of, you got to keep it to yourself and keep it secret. Share, and you're going to end up learning from others as well. And I think that'll expand your knowledge really rapidly. Last question for today. If people want to follow you and see what you're up to, how are they best to do so? What are your sort of website, social media accounts, etc.?
So our website is www.bournehpp.com, and our Instagram's probably one of the platforms that we're on the most, and that is Bourne_HPP. And yeah, that's the best place to follow us on racing, engine builds and tuning and everything that we get up to, really.
Great. And as always, we'll put the links to those accounts in the show notes to make it easy for people to find. Look, Terry, really great chat today. I really appreciate your time. This one has gone pretty long, but there was a lot to dive into, and I still feel like we've only really scratched the surface. So appreciate you coming on the podcast, and all the best for the future.
Lovely, awesome. Thanks for having us, Andre. It's been a pleasure.
If you enjoyed this episode of Tuned In with Terry, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks each week, we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have, and I'll do my best to answer them if your review gets picked. So, this week, a big shout out to Kevin B from Texas in the United States, who has said, "The gold standard automotive podcast. I've learned more from HPA's Tuned In podcast than I would have ever thought possible from an audio-only format." Well, thanks for the kind words, Kevin. Great to hear that you're getting so much value out of the podcast. And if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpaacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpaacademy.com/courses.